Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking back in time, like really far back, 13 billion years into the past, right to an era when the universe was just a tiny, tiny fraction of its current age.
Right, the cosmic dawn.
Exactly. And if you were to, paint a picture of that cosmic dawn, you'd probably expect pure chaos. I mean, you'd expect these massive, blazing structures, just violent, explosive birth of the early cosmos.
Yeah, a totally inhospitable environment, just full of raw, unfiltered radiation.
Right. But instead, the James Webb Space Telescope looked into that deep, ancient dark and captured something entirely different. Hiding way out there in the deep infrared, there are these tiny, faint, very red pinpoints of light.
The little red dots.
Yeah, astronomers have actually affectionately started calling them little red dots, or LRDs. And these little red dots are hiding a secret so massive and honestly so counterintuitive that is actively rewriting our understanding of the cosmos and, the origins of life itself.
It really is. I mean, the sheer incongruity of what we are observing with these LRDs is what has the whole astrophysics community reeling right now.
Because they're so weirdly small, right?
Extremely small. These are ultra-compact protogalaxies. And, when we say compact in an astronomical sense, we usually mean something just slightly smaller than average. But here, we mean they possess a radius of only a few hundred light years.
Wait, just a few hundred?
Yeah, a few hundred.
No.
To put that in perspective, they are infinitesimally small compared to the galactic structures we're used to studying in the modern universe.
Okay, let's actually map out that scale for a second, because I think the numbers can just wash over you if you aren't careful. Like, you really need to feel the physical size of this to understand the paradox here.
Oh, absolutely. The scale is everything.
Right, so the galaxy you and I are sitting in right now, the Milky Way, spans over 100,000 light years across. 100,000. It's this sprawling, majestic spiral.
Sprawling is the perfect word for it.
Yeah. And these LRDs are just a few hundred light years across. So the Milky Way is, a sprawling, massive metropolis spanning all the way to the horizon. These little red dots are, they're barely a single city block.
They're cosmic specks, just absolute specks.
It's hiding something big.
Yeah, that scale is crucial to keep in mind because it's what is inside that single city block that has completely stunned everyone.
The black holes.
Exactly. The observational evidence coming from James Webb suggests that many of these tiny little red dots contain central black holes of millions of solar masses.
Which is insane.
It is. We are talking about black holes that are incredibly similar in mass to the supermassive black hole sitting at the very core of our entire massive Milky Way.
Okay, stop right there, because the math on that is it's completely wild.
It doesn't seem to make sense, right?
No, because in a normal massive galaxy like our Milky Way, the central black hole is huge, obviously. But compared to the entire galaxy, like all the stars, the gas, the dark matter, it makes up less than 0.01% of the total mass.
Right, it's an absolute drop in the bucket.
Exactly. But if you're looking at these little red dots, the black hole is making up around 1/10 of a percentage point, or even more, of the entire protogalaxy's mass. That is a massively disproportionate fraction.
It's a huge ratio.
It's like, it's like opening up the hood of a tiny little golf cart and finding a massive roaring 10-ton freight train engine shoved into the chassis. It physically does not seem like it should fit, let alone function.
That freight train analogy is actually perfect. It captures the tension. And that incredibly disproportionate mass ratio leads us directly into a major astrophysical anomaly.
Because of the torque, right?
Yeah, exactly. If you take a massive freight train engine and shove it into a golf cart, you expect things to get incredibly violently destructive very quickly. You turn that engine on, the torque just rips the chassis apart.
It would shred it.
Right. So if you have an impossibly massive black hole crammed into a tiny early galaxy that is dense with primordial gas and dust, you would logically expect an incredibly chaotic, energetic environment.
You'd expect it to be tearing the place apart. I mean, it's sitting in a tiny, cramped space filled with material. It should be feasting on all that gas and blasting out unbelievable amounts of energy.
That is exactly the expected behavior under our standard models. But, and this is the kicker, that is what is not happening.
It's not tearing it apart.
No. These little red dots glow warmly in optical and infrared light, but when we look at them in highly energetic light, they are shockingly dim. Specifically, they are missing the X-ray emissions.
Missing them entirely.
Pretty much, yeah. They completely lack the high-energy radiation that is universally associated with growing supermassive black holes or, rampant explosive star formation.
Which is a glaring paradox.
Yeah.
A black hole that big, forming that fast just 13 billion years ago, should be absolutely screaming in X-rays.
It should be a quasar.
Yeah, it should be the brightest, most violent, most destructive thing in its local neighborhood, just sterilizing everything around it.
And this absence of X-rays challenges the fundamental mechanics of everything we thought we knew about black hole growth and galaxy assembly. I mean, how did these central monsters get so massive so quickly without emitting the chaotic, destructive energy of a quasar?
Because usually it's a messy process.
Very messy. The standard models of black hole formation involve a long, incredibly violent process of accretion. A black hole essentially eats surrounding matter.
Right.
That gas and dust spirals inward, forming an accretion disk. And as it spirals closer to the event horizon, it experiences immense friction. It heats up to unimaginable temperatures, millions of degrees, and blasts out intense X-ray and ultraviolet radiation.
But the LRDs are quiet.
Exactly, they're quiet.
So, okay, if they didn't grow by that messy, noisy, frictional eating process, how did they get there?
Yeah.
Because they undeniably exist. James Webb is looking right at them.
Yeah.
We can measure their mass.
Well, a really fascinating proposed solution comes from recent theoretical physics. Specifically, a formation channel explored in a 2025 paper by Ruffini and Vereshchagin. They proposed that these early massive black holes didn't grow slowly through accretion at all. Instead, they formed through the direct collapse of a self-gravitating fermion system.
Okay, wait, hold on. Direct collapse of a self-gravitating fermion system.
Yeah.
You can't just drop a phrase like that and move on.
Fair enough, fair enough.
We need to translate this because that sounds like pure science fiction jargon. What does that actually mean in the physical universe? How does a massive cloud of anything just magically bypass the immense friction and heat we just talked about?
To understand the difference, we really have to look at the subatomic properties of the matter involved. Let's start with the standard model of black hole growth, okay?
Yep.
Imagine trying to get 100,000 angry shoving people through a single narrow stadium turnstile.
Oh, that sounds like a nightmare.
Right? People are bumping into each other, they're generating heat, there is noise, there is friction. It takes a long time, and the surrounding area is just pure chaos.
Yeah, total bottleneck.
Exactly. That is normal baryonic matter, gas, and dust trying to squeeze into a black hole. It collides with itself. It generates intense friction, which creates the blinding X-rays.
Okay, so the angry crowd at the turnstile is the glowing accretion disk. Got it. So what is the fermion system doing differently?
Well, a fermion system in this context refers to a massive, incredibly dense cloud of subatomic particles that do not interact with electromagnetic forces the way normal gas does.
Like dark matter.
Yes, particles like dark matter or extremely dense degenerate matter. Let's use your stadium analogy again.
Okay.
Instead of an angry crowd of solid bodies, imagine a massive flock of ghosts.
Ghosts.
Yeah, ghosts. They all want to get to the center of the stadium, but because they are ghosts, they don't bump into each other. They pass right through one another.
Oh.
They don't generate friction. They don't generate heat. They don't emit light.
Oh, that's wild. So because they don't experience electromagnetic friction, they don't form that glowing, screaming accretion disk. They just fall.
They just fall. When this massive cloud of ghost-like particles reaches a critical density and mass threshold, the collective gravity becomes too strong.
And it collapses.
Exactly. The entire system collapses directly into a black hole. It happens almost instantaneously on a cosmic timescale. No accretion disk, no intense friction, no splashing, blazing radiation,
Wow.
Just a massive, silent collapse under its own gravity. It bypasses the slow, messy, and bright process entirely. The black hole is simply born massive without the chaotic X-ray fireworks we associate with gradual growth.
So the monster just suddenly exists, fully formed, massive, and completely silent.
Precisely.
That perfectly explains why the golf cart isn't melting around the freight train engine. The engine was just dropped in perfectly intact without ever being revved up to a roaring destructive speed. It just quietly slipped into place.
That's a great way to put it.
And the truly remarkable thing is that to understand how a massive black hole can be this quiet, this gentle, we don't actually have to rely purely on complex math about the earliest moments of the universe.
Yeah.
Like, we don't have to just theorize.
Yeah, we don't.
We can literally look at the center of the spiral galaxy we are sitting in right now.
Right. The Milky Way serves as an absolutely perfect modern-day mirror for this exact phenomenon. We have our own monster. At the heart of our galaxy lies Sagittarius, a star, a supermassive black hole that is roughly 4 million times the mass of our sun.
Which is terrifying to think about,
Yeah.
honestly. Just a 4 million solar mass gravitational sinkhole sitting there in the middle of our galactic home, quietly holding everything together.
It sounds incredibly intimidating, but Sagittarius, a star, is essentially a gentle giant. It is practically dormant in its current epoch.
It's asleep.
Yeah, it's asleep. It is accreting so little material right now that it shines at less than a billionth of its theoretical maximum luminosity.
Oblivion.
A billionth. If it were actively feeding, the center of our galaxy would be a blinding beacon. But instead, there are no massive jets of material shooting out into intergalactic space. There are no intense X-ray bursts sterilizing the galactic core. It is, for all intents and purposes, asleep.
And because the monster is asleep, the neighborhood immediately surrounding it is surprisingly calm. It's like a sanctuary.
Yes, a sanctuary.
Which brings us to this specific region in our galactic core called the Central Molecular Zone, or the CMZ. Because Sagittarius A star isn't blasting the area with those sterilizing X-rays, the innermost region of our galaxy is able to maintain this incredibly dense concentration of interstellar clouds.
It is exceptionally rich in cold gas and dust.
Yeah, and the environmental contrast there is the critical factor.
Oh, absolutely. When astronomers observe the galactic center, we do not see the highly ionized, incredibly fast outflows that are the hallmark of powerful active galactic nuclei in other galaxies.
Right, the violent stuff.
Exactly. We don't see matter being violently ripped apart and superheated by the black hole's magnetic fields. Instead, what we observe are low-energy emissions. We see the clear, peaceful signatures of ongoing, normal star formation and gentle, swirling, nebular structure.
This is chilling out.
It is a state of profound cosmic calm, resting right on the doorstep of a supermassive black hole.
But let's pause and connect this to the person listening right now. Because you might be thinking, why should you care that the center of the Milky Way is electromagnetically quiet? I mean, it's 26,000 light years away from Earth.
It feels very disconnected.
Yeah, it doesn't affect your morning commute. It doesn't change the weather. But it actually matters profoundly because a quiet galaxy is the absolute prerequisite for incredibly fragile things to survive.
And by fragile things, we are talking about the very building blocks of life itself. The organic molecules that form the basis of biology, water, methanol, complex nitriles, amino acids. These are structurally delicate at the atomic level. They are held together by covalent bonds that require very specific, stable conditions to form and persist.
They're picky.
Very picky. In the grand scheme of cosmic energies, they are incredibly easy to destroy. A single blast of energetic ultraviolet light or a wave of X-rays from an actively feeding black hole will dissociate these molecules in an instant.
Dissociate meaning?
Meaning the high-energy photons physically break the chemical bonds apart, reducing those complex organics back to just a useless soup of base atoms.
Okay, so imagine the galactic center as a massive industrial kitchen.
Okay, I like this.
If you have an active feeding black hole, your kitchen is pure, unadulterated chaos. It's like someone left a massive industrial blender running on the highest speed without the lid on.
Oh, wow.
You try to mix flour and eggs and sugar to make a cake, but the blender is just violently throwing the ingredients against the walls, tearing everything apart before it can even form a dough. Nothing complex, nothing delicate can survive that environment.
That's a great visual.
But if the black hole is dormant, like ours is, those molecular clouds act completely differently.
Right.
They become a sanctuary. It's like a quiet, temperature-controlled pantry.
A pantry.
Yeah. The ingredients can just sit there, safe in the dark, slowly coming together into highly complex recipes over thousands of years without being blasted apart by the blender.
That thermodynamic environment is exactly the dynamic at play here. These fragile, complex molecules naturally form in cold, dark environments. But they can't just form in empty space.
Why not?
Well, if two atoms collide in the vacuum, they usually just bounce off each other. They need a surface. They need the microscopic dust grains floating inside these molecular clouds to act as a physical substrate.
Like a workbench.
Exactly like a workbench. These dust grains, mostly tiny particles of silicates and carbon, provide a physical surface where atoms can gather, stick, and chemically react over tens of thousands of years. But, and this is key, those dust grain sanctuaries only exist and only function if the broader galactic environment is electromagnetically quiet.
Okay, let's dig into the mechanics of that dust grain, because I want to make sure the physics are crystal clear here. You have an atom drifting through the void at a high speed. It hits a bare rock, a dust grain. Why doesn't it just ricochet off into space?
Because of the extreme cold. In these quiet molecular clouds, the temperatures are staggeringly low. Because the dust grains are so incomprehensibly cold, they develop a microscopic layer of frost from the ambient gases, like an icy mantle.
An icy mantle.
When an atom drifting through space hits that frost, the ice acts like a molecular shock absorber. It bleeds off the kinetic energy of the incoming atom. The atom is caught.
Oh, that makes so much sense.
Right. It becomes trapped on the surface of the dust grain. As more and more atoms get trapped carbon, hydrogen, oxygen, nitrogen, they are forced into close proximity. The icy mantle holds them in place, allowing chemical bonds to slowly form, building up step by step from simple gases into highly complex organic molecules.
So the safe cold pantry allows for slow, meticulous cooking.
Exactly.
Okay, so the pantry is safe and cold. But a safe pantry doesn't bake a cake on its own. Do we actually see the ingredients mixing in there? Have we actually found these delicate recipes surviving in the center of our galaxy?
We have.
And the mind-blowing answer is yes. We're finding them right in our own backyard, in a very specific, heavily studied cloud of gas and dust.
The astronomical community has focused intensely on a cloud cataloged as G plus 0.693 minus 0.027.
Catchy name.
Very catchy. It is located just a few light years away from Sagittarius A star, right in the heart of the galactic center. This specific molecular cloud is incredibly dense and profoundly cold, hovering around 100 Kelvin.
Which is roughly negative 280 degrees Fahrenheit. It is a deep, deep freeze.
A deep freeze, yes. And crucially, observations show a complete lack of new stars currently forming inside the specific cloud.
Which is vital to the recipe. Because newborn stars are incredibly volatile, right?
Very volatile.
They are notoriously bright and put out massive amounts of localized ultraviolet light. So no new stars means no localized flood of destructive UV starlight inside the cloud itself. It is dark, it is incredibly cold, and it is completely shielded from radiation.
And shielded environments like this become astonishing chemical factories. Within this specific tranquil cloud, using advanced radio telescopes to read the chemical signatures in the gas, researchers have detected the distinct presence of nitriles.
Nitriles.
Yes. Nitriles are complex organic molecules characterized by a very specific structure, a cyanide group, which is a carbon atom triple bonded to a nitrogen atom.
A carbon triple bonded to a nitrogen. Okay, for those of us who haven't sat in an organic chemistry class in a decade or two, why is finding nitriles floating in a frozen cloud near a black hole such a monumental discovery? Like, what makes that specific triple bond so special?
It is entirely about what nitriles have the potential to become. In the chain of chemical evolution, nitriles are the direct essential precursors to RNA nucleotides.
RNA.
Yes. And RNA, ribonucleic acid, is an absolute cornerstone biomolecule for life as we know it. While DNA is the long-term storage of genetic information, RNA acts as the active messenger.
It's the worker.
Exactly. It carries instructions from DNA to the cellular machinery for controlling the synthesis of proteins. RNA is the molecule that actually does the work of translating code into biological reality.
Wow.
To put it simply, we are looking at a cloud of gas near the center of our galaxy, and we are literally observing prebiotic molecules. We are seeing the highly specific raw precursors to genetic material just floating there in the interstellar dark.
It's like finding a massive pile of incredibly specialized Lego blocks.
Perfect analogy.
Like, you aren't finding a fully built Lego castle. You aren't finding actual DNA or a living cell floating in the center of the Milky Way, but you are finding the exact, highly specific, interlocking blocks necessary to build that castle, manufactured and perfectly preserved in the vacuum of space.
It's incredible.
It really gives you chills to think about. It's the raw ingredients for genetics brewing in the dark. But obviously, a cloud of gas 26,000 light years away from Earth isn't life. So how does that cosmic pantry actually connect to you and me? How does a nitrile floating near a black hole get to a rocky planet orbiting a yellow star?
This connects beautifully to a foundational concept in evolutionary biology and origins of life chemistry known as the RNA world hypothesis.
Right, the RNA world.
This hypothesis suggests that life on Earth began with a simple, self-replicating RNA molecule long before the evolution of the complex DNA and protein ecosystems we see in modern cells. But a massive lingering question in that hypothesis has always been, where did the immense amount of complex organic material needed to spark that RNA world initially come from?
Because early Earth was a mess.
It was a molten, chaotic place. It wasn't exactly conducive to delicate chemistry. The answer seems to be falling from the sky. We have found many of these exact same complex organic compounds, these nitriles and amino acids, inside meteorites and comets right here in our own solar system.
So the comets are the delivery trucks, the pantry bakes the ingredients, and the comets drive them to the planets.
That is highly probable. The evidence suggests these complex molecules were cooked up first in those quiet, cold interstellar clouds. The Milky Way's tranquil core and other quiet, dust-shielded molecular clouds in the galaxy served as the cosmic kitchen.
Right.
Billions of years later, as our solar system was coalescing from a rotating disk of gas and dust, comets and asteroids forming in the cold outer reaches of our system incorporated these ancient pre-made chemical recipes.
They just scooped them up.
Basically, yes. When those comets bombarded the early Earth during its violent youth, they effectively delivered the meal. They dropped off vast, concentrated quantities of the prebiotic chemistry required to jumpstart the formation of life on our newly cooled planet.
Okay, so let's take this incredible process, this slow, safe, deep freeze chemistry happening in the Milky Way today, creating the building blocks of RNA, and let's project it all the way back 13 billion years. Let's return to the very beginning of our discussion. Let's go back to those tiny, mysterious little red dots that the James Webb Space Telescope found hovering near the dawn of time.
This is where the astronomical paradigm truly shifts.
Yeah.
When we analyze the spectral data from those little red dots, despite their incredible age and their microscopic size compared to modern galaxies, we find that the internal conditions are remarkably similar to our own shielded galactic core.
Really?
Yes. Their incredibly compact, dust-enshrouded nuclei maintain those exact same cold molecular cloud conditions. We're talking about internal environments hovering just a few tens of Kelvin above absolute zero.
So even though they have a massive million solar mass black hole right in the center of that giant freight train engine, because the black hole collapsed silently as a fermion system and is completely dormant, the surrounding dust is sitting in a peaceful deep freeze.
That is the crucial link. The dormancy of the black hole allows the extreme cold to persist. And in that extreme cold, the fundamental mechanics of interstellar chemistry take over exactly as they do in the Milky Way today.
These shock absorbers.
Exactly. Atoms and simple molecules floating in the primordial gas phase collide with those microscopic dust grains. The icy mantles act as shock absorbers. The atoms stick and the chemical assembly line begins. But there is an added advantage for the little red dots.
Oh. What's that?
Because these protogalaxies are so incredibly compact, just a few hundred light years across, remember they possess staggeringly high densities of gas and dust. There is an incredibly abundant, concentrated supply of raw material constantly colliding with the grains.
Oh, wow. So the grains are basically acting like microscopic, highly efficient workbenches. You have this extreme cold, locking everything in place, preventing the bonds from vibrating apart. And then over long, long periods of time, these simple ices react with each other step by step, building up into larger, much more complex organic molecules.
And the only reason they are allowed that time, the only reason this delicate step-by-step assembly isn't instantly reversed or shattered is the crucial lack of X-rays and harsh ultraviolet radiation.
Right, because the black hole is asleep.
Because those massive central black holes are quiescent, because they aren't feeding and screaming with radiation, these fragile, complex molecules are perfectly shielded by the dense dust. They survive, they accumulate, they evolve.
Well, wait, stop right there. You're painting a picture of this serene, peaceful chemical laboratory. But anyone who has read even a little bit about the history of the cosmos knows the early universe was an absolute war zone.
Oh, it was brutal.
It was notoriously violent. You had protogalaxies constantly colliding, tearing each other apart with gravity. You had blazing, massive young stars being born at ridiculous rates, living short lives, and exploding in supernovas that went off like cosmic flashbangs.
Right.
It was a chaotic, radiation-soaked infancy for the universe. How in the world could these little red dots stay so safe and pristine in the middle of all that external chaos?
It is an incredible juxtaposition, and it really highlights the unique physical properties of these structures. The universe at that time was indeed a volatile, harsh environment, saturated with energetic radiation from those early supernovas. But the dense, dust-enshrouded nature of the little red dots acted as an impenetrable physical barrier.
Like a shield.
A massive shield. The sheer density of the molecular clouds within them was so thick that it absorbed and scattered whatever external radiation might have threatened them. The outer layers of the dust took the hit, protecting the inner core. So while the universe outside was raging, and while their own central black holes remained remarkably well-behaved and silent, the interior of the LRDs remained protected. They were quite literally islands of tranquility, highly shielded vaults, existing right in the middle of a raging cosmic ocean.
Islands of tranquility, I love that image. A microscopic vault of cold dust, keeping the ingredients safe while the universe explodes outside. And if prebiotic molecules, the raw Lego blocks for RNA, were successfully forming inside these highly shielded little red dots 13 billion years ago, then we have to completely throw out the old textbooks. This entirely shatters everything the scientific community previously assumed about the timeline of life's ingredients.
It absolutely requires a total rewrite of the biological timeline of the universe.
Yeah.
For decades, the scientific consensus was based on a much slower, much later model of chemical evolution. The old assumption was that generating complex organic chemistry on a large galactic scale required a mature, settled universe.
We thought it took time.
A lot of time. We believed it needed several sequential generations of stars to live, fuse heavier elements in their cores, and die in supernovae just to create enough carbon, nitrogen, and oxygen to work with. We assumed you needed the vast, quiescent, slowly rotating niche of a massive, mature spiral galaxy like our modern Milky Way to provide the stable environment necessary for these delicate molecules to slowly evolve over billions of years.
We thought life's ingredients were latecomers to the party.
Oh.
We assumed the universe had to age, go through its chaotic teenage years, and completely settle down into middle age before it could even start prepping the ingredients for biology.
That was the paradigm. But the physical reality revealed by the little red dots changes that narrative entirely. It proves that the ingredients for life were not latecomers at all. They might have been assembled far earlier and much more widely across the cosmos than anyone ever dared to theorize.
Like almost immediately.
Yes. The highly complex chemistry of nitriles and amino acids was likely happening when the universe was only a few 100 million years old. This implies a profound shift in perspective. The universe was biologically fertile in its chemical potential almost from the very beginning. The capacity for life is not a recent, localized accident. It appears to be a fundamental, ancient, and deeply ingrained property of the cosmos itself.
So we have these tiny, ultra-compact proto-galaxies acting as massive, highly efficient chemical factories, brewing up huge batches of RNA precursors at the very dawn of time. But that raises the final and maybe most important piece of the puzzle. How does that localized cosmic soup spread out?
Right, the distribution.
Yeah. An LRD is a microscopic speck just a few hundred light years across.
Yeah.
How do those prebiotic seeds, locked inside a dense vault of dust, eventually reach new star systems and new rocky planets like ours, billions of years later?
The answer lies in the natural, violent evolution of galactic structures over deep time. As the universe aged and expanded, these tiny little red dot protogalaxies didn't just remain static in isolation. They are, by definition, the earliest building blocks of the universe.
They clump together.
Exactly. Over billions of years, the relentless pull of gravity drew them together. They merged, they crashed into each other, intertwining their dark matter halos and gas clouds, and were gradually incorporated into the larger, more massive galaxies we see today.
So they were basically swallowed up by the growing Milky Ways and Andromedas of the universe.
Yeah.
And when they get swallowed, they act like a cosmic payload.
Precisely a payload. During those massive galactic mergers, the incredibly rich reservoirs of complex organic molecules that had been safely accumulating inside the deep freeze of the LRDs were finally unlocked.
The vault opens.
The vault opens. As the galactic structures merged and spun around each other, the dense gas and dust of the LRDs were violently stirred, stretched out, and dispersed across vast new expanses of space. The mergers themselves acted as a cosmic distribution mechanism, seeding the newly forming larger galaxies with highly advanced pre-made prebiotic material.
Let's take that a step further, because the implications of that are staggering. If you think about it, macroscopic galactic structures, the collisions of galaxies themselves, were actively influencing biology before biology even existed.
It's a huge thought.
It is. The story of life isn't just a local story about Earth or liquid water or a lucky lightning strike in a primordial soup on a single rock. It is the story of entire galaxies baking the bread of life's recipe. The little red dots did the slow, careful, highly shielded baking in the dark 13 billion years ago, and then immense galactic collisions scattered those biological crumbs across the void, seeding the massive molecular clouds that would eventually collapse to form new star systems, new comets, and new planets.
The interconnectedness of it all is truly the most remarkable takeaway. How the macroscopic and the microscopic are intimately bound together. The physical behavior of a supermassive black hole, whether it feeds loudly or sleeps quietly, dictates the survival of a fragile nanometer-scale carbon-nitrogen bond.
It's all connected.
We have journeyed from tiny red specks hiding massive, silently collapsed black holes at the dawn of time, to the dormant giant resting in the center of our own Milky Way, and the underlying physical truth remains the same. We see that the most peaceful, unexpected, and even dormant places in the universe are the very chemical laboratories that made our biological existence possible.
It's an incredible realization, and it brings us to a really provocative thought, something for you to mull over the next time you look up at the night sky and wonder where else life might be hiding out there. In astronomy, we spend so much time, energy, and money looking for Goldilocks planets. You know the concept?
Of course.
Planets that are just the right distance from their star. Not too hot to boil the oceans, not too cold to freeze them solid, where liquid water can exist on the surface. We have always assumed that finding a planet in that habitable zone is the ultimate filter for finding life.
But if an electromagnetically quiet, completely dormant central black hole is an absolute requirement to protect the fragile chemistry of life from being obliterated by sterilizing X-rays, then perhaps a planet's location around its star is entirely secondary.
Oh, wow.
Perhaps the state of a galaxy's central black hole is the ultimate cosmic filter?
That completely flips the script. Maybe the real secret to finding life in the universe isn't just looking for Goldilocks planets. Maybe we need to be looking for Goldilocks galaxies, galaxies whose central monsters went to sleep early and stayed asleep. Galaxies that provided a massive, quiet pantry that allowed the earliest seeds of life to survive the dark. Because if that central monster wakes up, if it starts feeding and blasting out X-rays, it doesn't matter how perfect your little planet is. The blender gets turned on, the bonds are broken, and the recipe is ruined forever. It really makes you look at our quiet, sleeping giant in the center of the Milky Way with a profound amount of gratitude. And to think we first saw the fingerprints of this massive, quiet cosmic machinery hiding in plain sight, looking like nothing more than a few faint little red dots.